Not every broken JSON problem needs another retry loop. The real decision is whether to repair after generation or constrain the model before it fails. You'll learn how the pieces fit into a workflow that inspects a broken response and selects a targeted JSON safeguard. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. LLMs will sometimes emit almost correct JSON, a trailing comma, a missing quote, or a numeric field returned as text can break downstream systems. The question for engineers is practical. Do we accept the first output and repair it automatically? Or do we change the decoder so invalid structures never get emitted in the first place? Success looks like stable downstream pipelines, predictable latency, and fewer production incidents. At small scale, you might just fix the occasional broken object. At scale, you care about latency, throughput, and how many responses clear schema checks without human intervention. Intuitively, repairing is cheaper for rare errors. Constrained decoding is better when malformed outputs are common or expensive to fix later. A quick, concrete image. You ask a model for a JSON record with status and latency. If 1 in 20 responses has a trailing comma, a repair path can catch and fix those. If half your responses violate required types, adding checks during decoding often pays off. We will build a small decision workflow. It will try a straight parse, record failure details, attempt an automated repair, validate against a schema, and finally show a constrained decoding style guard that rejects bad partial assemblies early. Nothing fancy. The goal is clarity. See where each choice reduces incidents or costs you latency. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a tight parse guard that isolates decoding failures and preserves the raw LLM reply for debugging. This snippet shows how json.loads surfaces the failure details for an LLM reply that ends with a trailing comma. Broken JSON tends to hide until downstream services implode, so capturing the exact payload in raw reply keeps the incident reproducible. The tight try and accept around json.loads narrows the blast radius to a single place where you can branch into repairs or retries. Stashing exe.msg inside outcome preserves the human-readable explanation while letting you stream the value into structured logs. Because parsed exists even when the happy path succeeds, you can extend the branch later for validation or analytics without rewriting your guard. And the printed parse status confirms the monitor is watching the actual decoder failure rather than a secondary outage. That parse fence works, but it still triggers a round trip if you ask the model again. Next, we'll patch the payload locally, so we can avoid network retries and keep latency predictable. This example demonstrates how repair JSON patches the malformed payload without forcing another network round trip. Feeding raw reply straight into repair JSON with return objects equals true yields a ready-to-use dict instead of another JSON string. So latency MS can be inspected, logged, or aggregated immediately. Keeping skip JSON loads at its safe default lets you reuse the same snippet when later calls are already valid, minimizing unnecessary work in the hot path. Holding the repair dict in fixed payload also makes it simple to attach downstream schema checks or business rules without reparsing. The repaired latency MS print shows that your recovery path restored the numeric field instead of masking the failure. Repairing helps, but you only want to accept fixed objects that meet your contract. Now we add an explicit schema check and run multiple candidate fixes through it, so only valid objects advance. This code filters multiple payload variants through Draft 7 validator, so only schema-compliant data moves forward. The schema string pins status to the allowed OK enum and enforces an integer latency ms, mirroring the contract your downstream systems expect. By packaging the repaired object, a coerced latency, and a missing field case in candidates, you can see at a glance which branches survive validation. Draft 7 validator schema creates the reusable validator, and validator.isValid keeps the loop clean without having to inspect error objects on every path. The resulting valid payload count print tells you how many responses would actually clear your guardrails before they touch production data. Once you have a repair route and validation, the last pragmatic question is latency. Does checking and repairing add unacceptable delay? We can measure the trade-off with simple timing samples. This snippet compares measured latency samples for strict first parsing versus skip JSON.loads to quantify the savings from skipping redundant validation. The strict chain MS list stands in for timings collected when you attempt json.loads first and call repair JSON only on failure, while skip chain MS captures runs with skip JSON.loads equals true. Statistics.mean turns those sample windows into stable averages so you can discuss trade-offs with SRE or product stakeholders instead of arguing from anecdotes. AVG Delta reports the observed gap, making it easy to decide whether the specialized path warrants the extra guard conditions. These numbers are toy measurements, so swap in your own telemetry to confirm the pattern on real traffic. Repair and validation handle a lot, but constraining the decoder itself prevents malformed outputs and offloads work from your repair path. Here is a minimal approach that emulates token-level gating by validating partial assemblies as they grow. This example walks through a minimal constrained decoder that rejects invalid candidates before they ever reach the schema validator. IsPartialValid uses validator.iter errors but ignores required complaints, so partial assemblies can continue while still blocking type or enum violations. The nested loop walks each step's options, merges a candidate with the current payload, and commits only when the partial structure passes that check. Because we stop at the first good option, the pattern mimics token-level gating without needing a full sampling API, yet still guarantees the final assertValidator.isValid payload succeeds. The constrained output print proves the decoder surfaced a compliant object instead of emitting the first token sequence it saw. Mapping this toy flow to real systems is straightforward. Use the parse guard at the model client boundary. Run repair and validation in your transformer layer that prepares records for downstream services. Adopt constrained decoding for high-volume endpoints where errors are frequent and costful. Quick recap. This is a decision framework. Repair when errors are rare, and add constrained decoding when they're frequent. Start with repair for occasional glitches, and introduce constrained checks when you see repeated schema violations. One caveat: constrained decoding reduces errors, but can increase decoding complexity and development time. Next step, measure the real traffic and tune the validator threshold and the constrained decoder acceptance rule to your error profile. Try increasing the strictness until repair frequency meaningfully drops without harming throughput. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.